So Dr. Alonso Vera is the NASA Senior Scientist for Distributed Collaborative Systems and is a recognized expert in the fields of human-machine systems and artificial intelligence. Since 2000, he has led the development of new technologies at NASA for robotic and human spaceflight missions, including Mars Exploration Rovers, Phoenix Mars Lander, Mars Science Laboratory, Space Shuttle, International Space Station, and the Moon to Mars programs. Alonso received a Bachelor of Science from McGill, a Ph.D. from Cornell, and completed a Post-Doc Fellowship in the School of Computer Science at Carnegie Mellon. More importantly for me, while he was at Carnegie Mellon, uh, his wife met my wife as they were starting in the business school there, and they became great friends. And not long after that, Alonzo met Reese and married her. And then many years later, I met my wife Cornelia and married her. And because of that, I got connected to Alonzo, and he's now become a great friend of mine as well. So with that, happy to introduce Alonzo.
Thank you for the introduction, and again, thank you for inviting me. Just looking at this video, that space you're in seems very cool. It would be I'd enjoy visiting sometime. So what I want to do is take you through some of the work that we've done for the last 6 years or so on characterizing one of the challenges with a human mission to Mars, and then the approach that we're taking to it. And I say one of the challenges because there are a lot of challenges associated with a human mission to Mars. A human mission to Mars has been, an idea that goes, way back, obviously. And I'll put this up from Wernher von Braun from 1952. I'll talk about this in a second, but at the moment, and really for the last about, let's say 6 years, NASA has again had, it goes by different names at different times, but NASA has something called the Moon to Mars program. The idea that we're going back to the moon, we're going to use the moon as a testing ground to go on to Mars. And so there's an office called the Mars Campaign Office. That's what I'm currently working for at the moment. And there are a number of areas where, again, NASA is currently investing in a human mission to Mars. One of the questions that we often get asked is, if it's so hard, and I want to say this right up front, because part of what I'm going to say is sending humans to Mars is really hard. So one of the things that I think pops into people's mind right away is, if it's so hard, why are we doing it? Why don't we just send robots? And we can send robots, and we have sent robots, and we will continue to do so. There are a number of answers to that. One answer is that it's still the case that a human can do in minutes what it takes days, months for a robot to do. Another reason is that we often think, like, for example, let's say it's $1 billion to send a rover to Mars. We think that we're just basically taking $1 billion and putting it in a box and sending it to Mars. The actual cost of the vehicle, the rocket, the rover, is a small part. Really, the bulk of it goes into paying people who are experts to advance the technologies that we have, right? So this advances our technologies, and then we go on to actually understand better, the nature of Mars and the solar system and planetary formation, and right, so you get that relationship between technology and science. And then, another reason too is that, and this is really what I'm going to talk about, that going beyond Earth's vicinity, in which I'm including the moon and sort of Earth vicinity, is, again, it's a hard problem, and we're either going to try to do it or we're not as a species. And so if we are, then these little steps that we take now are the beginning of that, right? So if and I go back to here to this quote, right? So in 1952, and in fact, I think it was something like 48, 49, that von Braun wrote a book called The Mars Project. The Mars Project was really the kind of orbital mechanics, orbital dynamics that were required to. So it was a set of equations to get us to Mars. He actually thought that back then we could have done a mission to Mars, in part because again we'd come to understand how to get a rocket to the right place with some like reasonable degree of accuracy, and that is true. And we've been able to successfully land things very close to where we want to on Mars since the mid 70s, right? So quite a few years after this. Now the view back then, and a couple of things that I like about this quote. So he said right at the beginning, this is page 1, right? It's time to explode at once and for all, the theory of a solitary space rocket and its little band of bold interplanetary adventurers. It was learned thoroughly how some ridiculously insignificant incident can jeopardize the results of years of preparation. I'll come back to that point, right? This ridiculously insignificant incident. And then, he goes on to say the study will deal with a flotilla of 10 space vessels manned by not less than 70 men. So, the vision, and he goes on and talks about Columbus, right? 3 ships, 30 sailors per ship. On one ship, they could make masts. On another one, they can make sails. So there was redundancy of skill, of supplies, and then of ships that could take other sailors on if there was a problem. Here we are now, 2026. One of the things that is really, and I won't go into this, but is a reality, is that sending 10 ships or a very big ship like in the Martian, it is costly and technologically challenging beyond, I think, certainly beyond the capabilities of NASA by itself, but probably even as a global project, it would be very, it would be probably more difficult than we could do anytime in the near future, right? So we're still thinking of this sort of solitary space rocket with its little band of bold interplanetary adventures, right? So something like 8 astronauts on their way to Mars in one vehicle, and maybe 4 go down to the surface and 4 stay in orbit. And again, this is all being worked. NASA currently has a Mars architecture team working on exactly these, and people, myself, I've been supporting some of these decisions about how many crew, how do we, do that balance. And as I said, there are a lot of challenges. One of them, for example, is propulsion, right? So for now, pretty much everything in space goes at 17,000 miles an hour because that is breakaway speed from Earth's gravity well. So typically when we've sent something to Mars, it takes about 9 months because it goes at 17,000 miles an hour as it breaks away from Earth. There are, the designs, for example, there's a Vasmer engine, which is ion propulsion, nuclear engine. So we can speed things up. Those haven't been, tested in space. And but definitely getting there's in a timely way is a challenge. Radiation remains a very big challenge, not a big solution for that at the moment, right? Exposure to radiation, any amount of shielding is a lot of mass, which means, again, you got to get that off the surface. But I'm not going to talk about those issues. I really want to focus on one that is, again, I think quite interesting and a bit of a hidden problem. And it's a bit of a hidden problem in part because we all watch movies, in part because, we have this sense of astronauts, out there, flying the vehicle, like managing the issues. But the fact is that there's certain ways that we manage expedition risk on Earth. And what I'm going to go on, tell you just, quickly here is that that management of expedition risk, it all becomes challenged when we try and go to Mars, right? So take, for example, flying an airplane, right? So flying an airplane has, sometimes things go wrong. And so, from the very beginning, landing strips were set up all over the world so that you were never that far from being able to land somewhere, right? So, polar routes, et cetera. We've moved a bit away from that, but it's still generally the case that, a plane can, find a place to land under difficult circumstances. Now, as we've, over the last, say, 70 years, reduced the number of crew in the cabin, right? There was a time when it was 4, right? You had the captain, the co-pilot, a navigator, communications officer, right? Now, really we're effectively down to 1, and we have often, 2, for backup. But the way we do that is, we have air traffic control, and it's layered, right? You've got what are called centers, which manage flights as they're going between continents and between major areas, and they hand off an airplane to TRACON, which does, bigger areas, metropolitan areas, something like San Francisco Bay with its 3 airports, and then towers, which will then take over. And it's this very complex system that manages flight. And the minute something goes wrong, the response is very much on the ground too, right? Clearing an airport, say, for a landing, or getting expert support online. And so we've reduced the number of experts on board by making it so that expertise and help in an emergency is available. And on top of this, the longest flights right now, are 16 hours, 17 hours, 18 hours. I think, kind of Hong Kong to Chicago, those kind of flights are. And so short duration, and with the availability of support in case of a contingency. That's mostly how we did Space Shuttle. So Space Shuttle, again, a couple of astronauts who are the pilots, often a couple of other ones who can help, but really most of the troubleshooting and everything done on the ground. Longest shuttle mission ever was 17 days, which means that if things go wrong, unless they go really terribly wrong, you don't need to fix them. The shuttle would come back down and get maintained and repaired on the ground. In fact, it was one of the challenges with the shuttle, why it didn't fly more often, was because maintenance on the ground took longer in general, much longer than was anticipated. There's another engineering lesson in that, which is you got to design for maintainability, and that's always a trade-off. So you have this large support base on the ground, not particularly long mission, and they were able to evacuate. In other words, come back and land just like on airplanes, right? That you can get back on the ground in a short amount of time. Probably everybody knows this, but it's actually, when you're going up, it's about 8 minutes to low Earth orbit. It takes longer, of course, right? Because you're orbiting and you're coming in at an angle. But not, it's not hours. Once you're on your way in. Space station, you might ask yourself, well, that's been up there a long time, and it has. It's been up there, 26 years, and permanently occupied for 26 years. So what do we do there? Well, we have expanded support. The idea was that space station was actually going to be able to operate itself, that the crew members up there would be flying the space station, but in the end, that hasn't been the case. And the space station is flown from the ground, right? So it's commanded from the ground, orbit corrections, everything's done from the ground, the alignment of the solar arrays, and so it gets commanded from the ground. The data, the telemetry that you're watching to see if there are issues comes straight down to the ground. And then on top of that, again, there's reasonably quick evacuation. And evacuation, again, being able to get out and get to safety, right? And I'll go on to say this, but I don't want to forget to say it, that this, recently, you'll probably remember from the news that an astronaut had to come down, and in fact, the whole crew came down because of a health issue. That was the first time that it ever happened. that we had to bring an astronaut down for a health issue. And in general, in mission control, it used to be, for like Apollo, et cetera, you had your flight surgeon in the mission control room. Right now, like, you don't, right? There's not but you have a mission control room full of controllers who are keeping the vehicle alive, right? So humans have turned out to be fairly resilient in low Earth orbit, protected by radiation because the Van Allen belts are still reasonably effective in low Earth orbit. But it's the vehicle, and the vehicles has problems all the time. Okay, I'll go into, and big ones and little ones, but I'll talk about that. And so we can return, you can get off the vehicle quickly. And then the other thing is we resupply often. So if, for example, we are venting atmosphere, which in fact, the space station has been venting atmosphere, and there's been work to try and understand where that problem is, where we're losing, air. But we can resupply every couple of months. We send up more air, or we send up more water, right? So it's not effectively a system where if you were to lose any of your critical resources, resupply becomes hard. And I hope as you think about what I'm saying here, you're mapping all this onto Mars, right? So what happens when you really need to be down and for months, and you can't communicate, you can't ask for help, right? And attack submarines are an example of that. And we actually worked with a couple of people who spent years on attack submarines, learned a lot about it. What's interesting is if you have to be down, say 6 months, no comms, you bring everything, all your supplies you need. And in fact, the reason that submarines, these nuclear powered submarines, are down 6 months and not longer is because they run out of food. They eventually, come up for that, right? But on these submarines, you have in the order of about 140 sailors, and about half of them are doing the mission, surveillance, et cetera. The other half are keeping the submarine alive 3 shifts a day, 24 hours a day, for those 6 months, right? So you have a hydraulics team, you have a electronics team, the nuclear side, you have IT. So you talk to people, they're working in shifts, just 24 hours a day, keeping the submarine alive, right? So again, but you have in the order of 70 sailors doing that job. And you go back to Werner von Braun saying we're going to send about 70, and then you look at the fact that roughly the number of controllers, ground controllers at the Mission Control Center in Houston, if you look at 24 hours, it's about 70, right? You have 20 some people on console per shift, right? And interesting coincidence, but if you're going to keep a machine alive that is effectively keeping humans alive, and that machine is a complex engineered system, that seems to be roughly the number. And so our challenge, of course, is how do we do this for now a system that will have very few people? And again, here, this is an example of the Mariana Trench, right? What happens when you have to do something very dangerous, and you can only send a few people, you can't really escape. Well, you basically make it very short, hours. Most of these, where you're doing exploration of this sort on the planet, you do it for hours. So typically, you have a certain amount of expertise you need either on board or you need it off board, but you can communicate with it in real time, and that's really important. You can either escape or resupply, and if a lot of those are challenged, you make your mission very short. Mars is 9-month transit time to Mars. There's either a short stay where you stay for just a matter of weeks, 2-3 weeks, because of the way when Earth is going to come around. And so you've got to launch quite quickly to, get back to Earth, or you stay 2 years and then you have transit back. Very long mission. You can stage supplies on Mars before you get there. And, that's most of the mission concepts have that in it. But you're 9 months to Mars. You cannot, you can't resupply on the way. And I'll say a little bit about why escape is actually difficult. So Mars sort of pushes on every aspect of this. You don't have real-time support. You have a very small crew. Your mission duration is very long, and you don't have evacuation or resupply. And when we've looked at this, it is probably closest to something like the Amundsen expedition to the South Pole in 1911, where they went in with what they could carry. They couldn't ask for help, right? They didn't have there was no effective radio communication where they were. And now I think it's kind of gone out of my head, but this was in the order of like a month, maybe 90 days, something like that, right? Or maybe, but I think it was less. And of course there were two expeditions, right? So there's the Amundsen expedition and the Robert Falcon Scott's expedition, where they all perished and didn't make it. And there are interesting lessons in both. Just to note that one of the things that on the Scott mission is that they had developed some new technology, which were it was like a tank without the upper part. So they had the treads and a surface platform. And, the idea was, instead of having dogs drag their equipment, they had these, tank-like systems, and they put their stuff on it. And in the days before, maybe weeks before the mission started, one of the funders decided that he wanted to go. There's, a British person who provided a lot of the funding for the mission, and so they bumped the engineer who designed the tank tread system, the whole, that piece of equipment. And so when all three of those stopped working, they had nobody to fix it. But they're one among a number of issues. So just to kind of frame the problem, right? So one of the first things we did was look and say, okay, if we're going to do a mission this long for crew members, are there analogs, missions that we do that are similar? How do we do it on Earth? And what we found is we apply a set of, again, you either get help from the outside and real help, or you can have your whole team on board like you do on submarines. And if you can't have any of that, and you can't evacuate, and you can't resupply, you make it really short. And again, for Mars, it's exactly, all those things. So space station is about 200 miles above Earth. It's about 200,000 miles to the moon. It takes about 3 days. And it's about 200 million miles to Mars. It's about 9 months of transit time to Mars. And there are two issues with, like I said, one is with escape, evacuation, let's call it, which means coming back to Earth and then resupply. Because of the moving orbits, and because you're going at 17,000 miles an hour, or maybe faster if we develop, new engine technologies, to have something converge with you going in exactly the same direction on the path at the same velocity, so you can actually, grab it on the way, is very difficult. So there aren't currently concepts for resupply during the 9-month trip to Mars. So you have what you bring on board. Evacuation is interesting because you'd think, well, you can just turn around, but Kepler's law. So Earth is moving a little, faster on its inner orbit, moving in short amount of time around the sun. So we launch as Earth is coming up to the sun. And what happens is that about a month after launch, out of those 9 months, about a month after launch, the vehicle can turn around and start heading back. But the problem is Earth has moved away quickly enough. And so after about a month on your way to Mars, it'll be a year to get back to Earth, because you have to come in, you have to head the other way and have it meet you as it comes around its orbit. So that is the evacuation challenge. You have in the order of 20-minute max one-way communication delay when Earth and Mars are close to opposite, on opposite sides of the sun. It's about 7 minutes when they're at their closest, one way. So you're going to have between 7 and 20 minutes communication delay one way, between 15 minutes and 40 minutes two way. And if you have a problem, it is going to take, let's say, in the order of half an hour to an hour before you start like really getting answers beyond, yes, we understand you have a problem from Earth, right? And this is this problem of Earth independent operations and the fact that we have really not had to do Earth independent operations so far, right? So even on the moon, and those moon stays were, the longest moon stay was Apollo 17, and that was just about 3 days. And again, they didn't try to fix things. We had actually the pleasure of talking to Jack Schmitt, who was one of the last two astronauts on the moon, right? So he was Apollo 17. He was the geologist. He was the only scientist that went and set foot on the moon. So about 4 or 5 years ago, he's one of 4 Apollo astronauts still alive, and he talked to us. And he said by the time they left the moon, nothing worked. Nothing plugged into anything else, nothing open, nothing unscrewed because of the lunar dust, right? So the environments are harsh, certainly on surfaces. But again, they didn't have to fix too much. They just had to come back, right? So longer duration, we're going to have to fix things. And that is something that we haven't done. And even on the space station, we don't fix things. We replace the whole unit. Why? Because we can get one up there, in a short amount of time, right? So if a pump breaks, we send up a whole new pump assembly, pull it out, we put in the new one and send the other one back. So these are the challenges that start emerging when you start looking at 20 minutes of, so everything that the ground now does in real time, including monitoring data, so situation awareness, then this diagnostics and troubleshooting, and then oversight and guidance of execution of procedures, which is a lot of what the crew are doing. Is they're not up there, they're going to be very busy, is executing procedures, right? Probably a lot of it being maintenance and repair, like on submarines. And by the way, one question that I sometimes get is, what if we make the vehicle really, really reliable? And it turns out that reliability, if you look across systems, complex engineered systems, we're good engineers. We're not perfect engineers. You just don't anticipate all the problems. So we can't get all the problems out. And the harder the environment and the more unpredictable and the more untested it is, the more that is a challenge. But we basically looked at aviation, at trains, at nuclear power plants, at power grids, and you basically find that yes, there's a rate of incidents and accidents that you never get it down to zero. It's just the nature of engineering. So 2 to 3 year mission duration, right? So again, going back to those slides I showed at the beginning of just how hard this is. So we're only going to be able to bring probably, like I said, maybe 8 astronauts, 10 astronauts on the way there, if the vehicle can be big enough. So if we're currently doing it with 70, we're trying to get down an order of magnitude the number of humans. And that's a big reduction in expertise. And basically on the ground, the depth of expertise in terms of ground controllers is remarkable. To become a ground controller is, we hear this often, is equivalent to getting a Ph.D. It is a lot of experience in each controller. So how are we going to do it? And what is the challenge that is ahead of us, right? Because if it were true at this point that, well, there really aren't that many problems that you encounter, their chances of maybe having a big issue is, say, 5% on the way there, 9 months. Okay, there's some amount of risk you have to accept. And that's another thing that, talk about often. You You accept a certain amount of risk. An important part of accepting risk, by the way, is always understanding risk. You don't accept risk without understanding and quantifying it. But so we went about the quantification here and said, okay, let's understand how often anomalies happen and what they're like. So we're interested in unintended or basically off nominal, being not normal states in the vehicle, right? So things you didn't, you unintended, like this wasn't supposed to happen, right? Or yeah, this is weird, this is broken, or and you may not know. And we're particularly interested in those that affect critical systems. Critical systems, almost by definition, include the environmental control and life support systems, those we call ECLS, environmental control and life support systems. ECLS systems are the carbon dioxide removal assembly, the water processing assembly, so it's all the systems, thermal controls that are keeping the biological systems on board the crew alive. And then other systems are also critical, right? Like the power system, right? Because it's obviously feeds everything else, structures and but typically it is the ones that affect critical systems that deplete essential resources. So for example, if you're somehow losing water, and again, if we're losing water on the space station, it's okay, we can send water up. If you're losing water on your 9-month trip to Mars, that's a big problem. And then also, in particular, those that involve uncertainty, where you're not sure what's happening, right? So we looked at the International Space Station, and we also looked at Apollo. I'll show both sets of numbers. And what we found is that over the past 25 years or so, in fact, this is actually just 2000 to 2020, and what you see here in blue is the total high priority anomalies that affect critical systems, and require diagnosis, right? So high priority is like, okay, yeah, let's, and again, not anticipated. We didn't see this coming, right? So, roughly 68 over the last, over 20 years. And then we went and looked at those and we said, of those, how many urgently required diagnosis? That really where it was all hands on deck, right? Everybody jumps on it. And that was about 38. So roughly 1.7 per year. And you see that in the early years, it was higher. And that's very typical of engineered systems. You have this bathtub effect. Luckily, we're not seeing the other end of the bathtub yet for space station. But at the beginning, you've got a lot of problems because you don't know the vehicle yet. And a lot of things are still being tested and you haven't gotten the kinks out. So close to 4 times a year of these major anomalies that would have, by all measures of like, given the significance of them and how they unfolded, ended badly were it not for the ground being able to control them and understand what was happening, stabilize the situation, and then go and diagnose it and figure it out, right? So that you have your 70 ground controllers on the ground over the 24-hour period, watching the telemetry, and each controller is sitting there in the front room, what we call the front room, which is the one typically that we see in movies, right? That and looking at typically like really very close to raw telemetry screens to detect problems early, to look for patterns and look for covariation, to talk to each other, and then to as soon as things start happening, to start working out, okay, what could this be? Is this something we've seen before? Let's okay, try starting that up again, right? That is how we do it. We also looked at what are called class 2 alarms. These are interesting because class 1 alarms are an emergency. Okay, so fire, a rapid depressurization, or something toxic in the cabin. Those 3 things, right? So something in the cabin will kill you, or a rapid depressurization, or something, or a fire. In none of those cases are you trying to diagnose it. The crew just safe themselves. They will go into a separate compartment. They'll don special equipment, right? So now class 2 alarms and you see the definition at the top. This is the actual definition. Indicate that crew or ground needs to take immediate action to avoid injury or death of crew or damage to ISS, the International Space Station. On average, with a very high number right at the beginning, almost 30 of those a year. So, if, of course it's on average, but, roughly you spread it out, it'd be almost every 2 weeks. You have an alarm that actually goes off, like, sounds on board and on the ground, saying that you have an event that you have to take immediate action to avoid injury or death, right? Or damage to the vehicle. And if you think about it, so a lot of these turn out to be, like it's it gets controlled quite quickly. It's a known issue, or so these turn out they're not false alarms, but they're a lot of these are again they're not like the slide I showed before, where those were really serious problems that really could have ended badly. Here, these are generally these are just alarms. This is the situation, and then you restart something. How do you know that? Because the ground, with this, again, 70 people on the 24-hour cycle, like very quickly jump on this and look at it and go, yeah, it's okay, we got it. And right. So again, this is in a sense a better indication of the workload that's going to happen on board, right? Is, like every 2 weeks, you might have an event that says, hey, like take immediate action. So what we found was that the incidence of this is high, and then some percentage of these, the slide that I showed before indicates, it's the proportion of those is also unacceptably high. 2 times a year that it actually you have bad events that really could have ended badly. Apollo, interestingly, even more, right? So they had an average of 3 significant incidents per mission, right? That affect critical systems, weren't anticipated, and required diagnosis. And again, those missions were in the order of, the longest one was about 12 days, right? So 3 big ones, right? And of course, we know Apollo 13, Apollo 12 was hit by lightning on the way up. Almost every mission except Apollo 17 had some significant issues. Apollo 17 was actually quite a, like said it was probably the cleanest mission in terms of not having like really hard things happen. So this is, like I said, it's typical of complex engineered systems, and is particularly true when you're doing more challenging things into environments you haven't been in before. This rate for Apollo is higher in part because you were, docking vehicles in orbit, descending to the surface, working then in an environment with very difficult, sharp dust. The dust on the moon is very difficult for mechanical systems, and then coming back up and redocking. And so the more complex the operations, the higher the number of events that happen. So this sort of analysis hadn't really been done before, right? To look at, okay, how often does this stuff happen that we're going to have to worry about, that, for now the ground handles. And when I said before that in some ways this is a bit of an invisible problem, again, we tend to think of, astronauts, and astronauts, by the way, do a lot, and they are often involved in these things. But like the fact is that a lot of the expertise on the systems and what we do about it, and the troubleshooting and the generating of procedures, happens on the ground. This is a really interesting thing, and I just want to. It's one of those, like, I find interesting nuggets that it's kind of worth putting out there. In 2013, the National Transportation Safety Board had a study done, and one of the little things that they found was that they went back and looked at major incidents and accidents in aviation. They said, okay, let's look at all of them. 40% of them turned out to be because of a failure mode that was unanticipated in the design process. In other words, 40% of major incidents and accidents in aviation were something that you didn't think of. And so when it happens, you don't have a procedure, or there's no software there to catch it, or there's no hardware there to back it up, right? One sensor fails and, you didn't think, oh, like what happens then, right? And so I, that number stayed in my head. uh, I think maybe the first time I saw this was at a talk in probably, let's call it 2014. Then in 2023, so a decade later, the senior software fellow at NASA, Lorraine Prokop, not aware of that other study, she went and looked at basically software issues for launch systems, crewed and uncrewed. And there was this 40% again, right? And then we started poking at it. We started talking to people on submarines, aircraft carriers, nuclear power plants, anything where you had safety critical. And they're like, yeah, that sounds about right. About half the time you get to a problem and it's either one you haven't seen before, or you've seen it before, but it's presenting itself differently and you need to come up with a different solution, or it doesn't look like one you've seen before, but it is, right? So one way or another, right? So about 40% of the time, and you realize, right, like that is a huge problem, because we're not going to solve this problem with kind of expert systems where we take all our, kind of that view from the 80s and 90s and 2000s, of AI, for example, providing us the ability to go and capture the expertise that's in humans as a set of rules, right? If you remember with expert systems, right, we weren't going to need doctors anymore because we were going to basically take, all the knowledge out of a doctor's head and put it in the system, and we would just feed it the symptoms and it would give you an answer. And those systems turn out to be both brittle, but I think very much affected by this 40%, right? The fact that things don't either present themselves in the right way, or again, they one way or another, your rules don't quite work, right? And so this was our challenge, for a long time, right? That in terms of, for example, what AI could do to help us here. So before I go there, I just want to say something about the ground response capability. I'll speed up a little. So we have about 22 consoles. You see the picture there in the middle is the Space Station Mission Control Center, about 660 years of cumulative relative console experience. There are these mission anomaly resolution teams. They're called MARTs. You see this on the left, about 747 years of experience in one mission anomaly resolution team. Of the teams, about 80% have engineering degrees, 24/7 support. You're monitoring about 30,000 data points, coming down about every 10 seconds. Space station actually has about 300,000 sensors, more like, once a second, or in fact, some like the power stuff, even kilohertz, right? So 1,000 times a second, but we don't tend to pull it down at that rate. So we, and then you have specialists on call, and about 70 controllers, as I've said, kind of working across these daily shifts, right? So this is how we do it. How are we going to get this into an order of magnitude fewer humans? And these are the, kind of numbers of just the magnitude of how we do it on the ground. And then we have all these engineering processes, right? We have, the training, the decades, long monitoring and support, right? And all the data we have from that, all the mission planning and flight history. We have modeling, we have detection, we have orbital laboratories, right? We have like procedure development and execution, right? So we have all this, but as far as we know, this covers like about 60%. And then the rest of it is very expert humans deploying exactly what that like human expertise often looks like, which is very hard for us to operationalize and turn into, again, like rule-based AI systems. So going back to that quote from Werner von Braun at the beginning, right? Mitigating the risk of a ridiculously insignificant incident. He called it a ridiculously insignificant incident, but really I think it's that 40%, right? It's the idea of a thing that you overlooked. A thing you didn't, or overlooked might be the wrong word, right? I mean, again, we're very good engineers, but you don't think of everything, of every possibility, of the interaction of every system with every possible other part, right? It is just fundamentally part of designing complex machinery. So what do we do about it? So we can take all our engineering and operations and our models and analysis and drawing, which are basically, and then your 70 or so flight controllers, context awareness, adaptive problem solving. This is, we have this. And the part, I'm not going to go into like in a lot of detail. I don't necessarily think it's interesting, other than to say that in 2012, with the advent, Hinton and convolutional neural networks, right? Everything we're seeing kind of in AI today, the AI that we had up until 2012 was one type of AI, and really almost everything we're seeing today is transformer architectures, right? And so what is it that transformer architectures do, right? Basically, they look for patterns that we don't necessarily tell it what to look for, right? So if you know anything about language research, right, you have people like Noam Chomsky who spent decades working on a universal grammar that might work across all languages, right? Because something like that was feeling it had to be programmed into our human brains, because we seem to acquire language like as if we have a language center in our brains. What was that mechanism? And then a lot of AI work went into that. And what's funny is that we basically solved that problem and then kind of got around, the Turing challenge, right? That, if it sounds like a human and behaves like a human and you can't tell it apart from a human, by basically just exposing neural networks to enough language data that it can generate very reasonable sounding, excellent, language. So those patterns were just pulled out of the data. But this really started with work on vision and imagery data, right? So the early stuff was done, can you show one of these convolutional neural networks a lot of pictures and have it detect what's a cat versus a dog, or cat versus not a cat? And that was, if you remember back in 2012, one of the early successes. And then, the AlphaGo, and, more recently, the Nobel Prize, went up to the protein folding, right? So anywhere where you have pattern and you can just pull out that pattern. And by the way, that's why these systems are being very good at computer coding too, right? Computer coding is a language. There's a pattern. You can go and you can, and you can come back and generate it very well. So we said, okay, what if we apply this to telemetry? But not just that, right? So apply it to telemetry to try and get at the more unanticipated, these like that 40%, the stuff that you didn't think of. One thing that's going to have to change for us at NASA is sensor technologies. And up to now, NASA has been, every ounce matters, right? Because of again, Earth's gravity well and the cost of launch. So mass matters and power matters. And sensors historically have been, they're powered, they're wired, and they have mass. And so we're very, very careful about what we, like how we censor things. That world is changing, right? So I was at Daytona Beach at that 24-hour race. In fact, I wasn't at the 24-hour race. That's a good way to get fired as a civil servant. We were there the day before the race and met with a lot of the teams. And one thing that they said is that the amount of data coming off each race car now, that has gone up 50x in the last 5 years. So 10x per year, right? So we have 300,000 sensors on board a vehicle that was, built in the 90s. And I could give you lots of examples, but basically sensors have changed dramatically, right? Low power, no power, you flash them with a photon and then they'll give you an answer. Very low mass, very modular, very interchangeable. Space design is a very heritage-based business, in part because it's so hard to test it in space. And so we tend to design things that we know have worked in the past. But sensors is going to be one of these new challenges where effectively, probably we're going to want vehicles that are, sensors, flying sensors, right? Just like our airplanes and cars, everything's turning into a computer with wheels and a computer with wings. So this is one of the ways that that we get to Mars is changing how we think about sensors, doing that machine learning on board in real time, and then tying in our data sources. So space station historical data, for example, right? Analog software simulations, and I'm just giving examples here of software simulations, for example. Another big area right now is what people refer to as digital twins, right? So you build a digital representation of a vehicle and you actually feeding it the real telemetry that's coming down, and you have it, basically respond. So you have a digital twin of that system. Digital simulations always have a problem, right? And you've probably heard this quote, I don't know where it came from, but which is that the problem with simulation is that it's doomed to succeed. And the reason is that we program it to do X, and then it does it, and then we're happy about the fact that it does it. But the real world is much less like that, right? So the real physical world, half the time we're trying to build a physical water processing assembly over here, and the digital twin, it is much easier to do that digital twin. The physical one, you'll spend months saying, I don't know why this dumb thing isn't working, even though it's in our lab, right? And we're just trying to build a physical thing, and yeah. So but our goal is to kind of pull this all together into an integrated approach. And I won't go into this. This is like us particularly taking, may I say an interesting thing here. It turns out, we didn't quite realize this for a bit, but the power systems on board are very, very valuable, more valuable data-wise than a lot of other systems, because they're like the circulatory system. So the power systems don't just carry power to, for example, power the motion of a pump. They will also carry signal about the state of that pump, right? So if a pump starts behaving differently, you'll see that signal in its draw. And so we've started in particular over the last year doing the machine learning on the power systems, and sure enough, you can start finding signatures of problems that you didn't see coming, right? And you're like, and so our challenge then becomes, how do we tie this to traditional AI rule-based systems that can tell you, right, with that additional information that you're getting from your machine learning systems, plus my traditional rule-based AI systems, plus my simulations that are of like the digital twin, and then fundamentally plus the crew. We're assuming that humans are probably still going to be, perhaps the most intelligent systems on board in their own way, intelligent, adaptive, flexible, and they need to be part of the system. And all of this needs to happen in real time. And this real time thing, and maybe, let me just pop here. I said crew interaction. I just don't want to take us too long. Where we are at today, and one of the things that we conceived of just this approach, and again, I don't know that it's particularly insightful, but the effort of bringing together the different kind of modeling approaches, including machine learning in real time. You don't know, like, is somebody else already doing this? Is this already happening? But over the last couple of years, it became clear that no, this is sort of AI frontier right now, the real time aspect of it, right? And last year, I was invited to give a talk at a meeting that was organized by Department of Energy. It turns out Department of Energy is the branch of the government that is doing, like, they got really the bulk of the funding to do AI work. And there were a whole bunch of other teams there, some of them looking at fires. And in fact, there was a team who had provided models based on this sort of integration that we're looking at here to both the Palisades and Eaton fire within 5 minutes of really the crews and the fire chiefs and people getting there. And they knew that those first models weren't going to be great, but better than nothing. And then, with every passing, 10 minutes, 15 minutes, your models got better. As you were getting, more telemetry off satellites, more off the sensors, more input from people in the field. That idea of real-time AI modeling and integration across different types of input, right? So not just sensor telemetry input, but then, analysis of terrain maps, and analysis of density of housing, and analysis of where you've got your people right now, and then analysis of input from people in the field. All of that integrated in real time, and so this has become literally in the last year an area, and it's I didn't come up with this name. It's great. It's urgent computing, and the first there's a special issue of the journal. Computing and Engineering, it's IEEE journal on urgent computing, and we have a paper in there in part because I think there was, and it felt for us very validating that that our approach, I think, is in line, and that we're, I think, along a similar kind of success and challenge path as these other teams that are working in this kind of emergent area at the forefront of AI, which is real-time interaction with all these different kinds of data and humans as events evolve, and how do you actually support that decision making and problem solving and situation awareness in real time. So I'll stop there. Hopefully that was interesting. That was my goal, is to kind of tell you a story that seemed interesting, and if questions, thoughts, be glad to hear them.
Thanks very much, Alonso. Are there questions from the audience? Anyone? Dave?
Do I need to be up there?
Just talk. You're good.
Okay, I was wondering about space debris. Obviously, that's an issue, I guess, traveling in interplanetary space. Do we have enough data from our interplanetary satellites to sort of assess the risk of space debris?
Did you hear that, Alonso?
It's a little hard to hear. Do you want to just
Yeah, Dave was asking about, he was asking if we have enough data to analyze and address the threat of space debris, any impacts that there might happen during that trip.
That's a good question. We haven't had any significant impacts, and of course, again, low Earth orbit and missions, but for the rovers that we've sent to Mars, so debris hasn't actually been a problem. And in fact, in low Earth orbit, it would be really debris from other, human-made systems up there, and at some point that will become a problem. But yeah, that space turns out to be very, very big. So far, it's a low incidence problem so far.
Great, thank you. Other questions? Greg?
So you had mentioned the issue with radiation exposure to the crew. You're going to be out there 2 to 3 years. I imagine there must have been sensors out there with all the projects we've had. All the visits to other planets, like what we set up. I mean, what does it seem like? What are the results from those probes? What do they tell us about radiation?
Okay, so if I understood the question right, so we put lots of vehicles out there, robotic, et cetera. And of course we do, right? We sent things to Venus, to Mercury, to Mars, and so what do we understand about the radiation out there in the solar system? That's the question?
Right, and I mean, it's probably just there are bursts, and they're probably constant measurements, degrees of radiation, and they're probably bursts that happen occasionally. I'm just wondering if, I'm sure that's been analyzed in some way and the risks assessed.
Yeah. So again, in low Earth orbit, right, you still have the Van Allen belts protecting you. The moon has, so the trip to the moon has a lot higher exposure. Those are the order 12 month, 12, 10, 12 day trips. we know that once we get out, just a couple of days out from Earth, the radiation environment is significant. And we also know that solar events, right? So solar storms will cause significant increases in radiation that again would be really problematic for crew. And so yeah, the amount of radiation, say, that you're exposed to in the solar system, it's well understood. I think our main challenge with radiation is that there aren't great ways to protect from it for humans, right? So we can shield, say, that critical aspects of computer chips, and there's work on high performance space computing, and those are rad tolerant chips. So either you have redundancy where you can take a radiation impact and you don't get a problematic bit flip. Biological systems, it's different, right? So it is an unsolved problem. And I was at a meeting about a year and a half ago, and one of the presentations was about a new approach to curing cancer. And I sat there and I listened. I thought, oh, it's interesting. Like, again, you hear kind of these kind of things somewhat often. But the person sitting next to me was a NASA headquarters person, and I was a little surprised. He said, well, like if that's the case, right? If we really can, cure this, then we're less worried about shielding. And I hadn't thought of it that way, right? But yeah, so one way or another, we're going to have to mitigate that problem. But I'm probably, so I'm not like a radiation expert enough to tell you, like what, say, the levels are out there. But I do know that one of the things that's at work, and that we're kind of working to take in ourselves, is when there are solar events, how do you prepare? So the crew would have to safe themselves. How do you get that information out there as quickly as possible to give them time? So that is something we've been working with, and a lot of that expertise is at Goddard Space Flight Center in Maryland, and so members of the team there working on Goddard's done a lot of the work on heliophysics that we are bringing to bear here.
Other questions? Or on Zoom, is there anybody on Zoom who would like to ask a question? If not, I'll jump in with one. Alonso, I'm looking at the numbers and looking at the math. We're going out orders of magnitude farther than we had before. Our sensors are getting, as you were describing it, getting orders of magnitude better and more thorough, but yet we're still left with this 40% unknown unknowns number, and we have essentially uh, a much harder problem to solve. And when you put all those together, I mean, does it converge to a point, or do you see it converging to a point where this actually can be accomplished in the near future with an acceptable level of risk? And and then I guess another question is, what's that acceptable level of risk that essentially is being designed for? And obviously, if you want to get down to less than 1%, you have to be a lot more rigorous and build in a lot more redundancy and a lot more safety than you would if you're willing to accept 10%, et cetera. So with that, I'll throw it back to you.
Yeah, that's a great question. And I think there are two parts, right? So one thing is that, Mars will obviously bring even, harder challenges than what we have with, say, Space Station or what we have with Apollo. But we do have a sense of the capability that it is required to keep the risk at a level that we find acceptable, right? So, with Space Station, we have not had any, events that have turned out badly. That's me knocking on wood. So we have a sense of, okay, it's roughly this much, right? So, right, and that 70 is a proxy. I think 70 expert humans around the clock that's about how much it takes to remotely keep a system alive, right? So we're about, say, order of magnitude off. A really important thing that's interesting, and that I didn't mention, and I probably should have, and Rod, so your question's perfect. What's interesting, when you go back and you look at that 40%, and this has been done, this was done in major anomalies and mishaps, there's almost always an investigation, right? What happened? It was a close call, or it was you go and you do a mishap investigation board. Be it, so the NTSB does them, right? NASA does them, DOE does them for so you go do these. What's interesting is that 40% is mostly not unknown unknowns. If that 40% were all unknown unknowns, then I think that the road ahead would be very, very difficult, right? That we would have no perch on that 40%. What you find is that 40% is mostly made up of unknown knowns. It is in your data, but you can't see the pattern. So when you go back and you do a mishap investigation, you go, oh, yeah, look, we had seen evidence that the O-rings had frozen, or we had seen evidence of this sort of strike before. We had, right? And so it is in your data, you can't see the pattern. And that in your data, you can't see the pattern is exactly what, in a sense, machine learning buys you. Now, the problem is machine learning by itself doesn't buy you necessarily an understanding of the problem. It's hard to map it onto the physical systems, right? It's just detecting patterns, right? Which is why you need to pull things together. But it's that change that I think really, and that insight, so understanding that we're targeting that 40%, but understanding that 40% is largely made of unknown knowns is what makes it so that, when I think with, again, changing the way we think about sensors, changing the way we work data, finding ways to do the onboard computing, which in itself will on the scale that's needed. So there are a whole bunch of challenges, but really the key and what we're working on now is to demonstrate that we can catch a reasonable, like we can get that from 40% to say 5%, which of course would be like an enormous success. But to bring it down to a level where it's an acceptable risk.
Got it. So that's what makes the problem tractable for the most part. So with that said, then it's really then it's really coming down to, can we change, our systems and our approaches so that it's really changing the way we do work then, or the way these things have been done in the past. So basically getting all that working for the very first time, maybe not for the first time, but more or less for the first time to that extent when we go out there.
Yes, and exactly. And then making it all actually be able to happen in real time, right? I mean, we can, we can do this not in real time, some of it. Mm-hmm. And it's also, again, I could have probably given a whole talk on how AI systems really currently are not interacting with humans in particularly interesting ways, right? They don't, no large language model actually goes and changes its foundation model based on interacting with you, right? It is, it's using the foundation model, but it doesn't change it, right? And it's a bit like humans with short-term memory and long-term memory, right? That if, I keep a lot of stuff just in short-term memory and and then it's gone, right? And that's in a sense how these systems work. And so we have long-term memory, and once in a while you got to put something in long-term memory, if your wife tells you, oh, don't forget to ask your brother, blah, 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 because, he might be sad about the fact that the dog died, right? Now, my wife would say that, of course, I don't change my foundation model either, but, I think, so we are able to go and change long-term memory. And that is a thing that is I think coming in this, is that real-time interaction where a human says, no, I'm observing this, or could it be this? And that the model really doesn't just kind of work it out based on, but it can change its assumptions in a way that, say, humans do when interacting with each other. That's important, but also not just in terms of humans, but then other data, like other in the face of engineering analysis that's been done, right? The big challenge is pulling all these data sources together. And again, that's something that is harder than it looks, but not impossible.
Let me just ask one more question then. So if the unknowns, is the unknown unknowns really then just 5% of that? Is that what that data showed too? Or how big is that unknown unknowns?
It's hard to estimate, right? So unknown unknowns so far, I would say I have in my career, and I've been on mishap boards, I've yet to see an unknown unknown. And we often, if you're like a center that had a mishap and you lost a vehicle, like, a satellite that, cost some amount of money and it went dark, you really hope it's an unknown unknown, right? That it was effectively an act of God, right? That it got hit by some, lightning bolt from Venus. And we're like, hey, that's an unknown unknown, right? Look, we didn't know Venus could even produce lightning bolts, right? So it's like we've never seen it before. We didn't even know that it could happen, right? That kind of thing is right. And so, it's like if you look at history of mishaps, incidents, accidents, they're exquisitely rare. Like really, I don't like honestly, and like I've spent time. I don't have an example of an unknown unknown.
Okay, so that does really make it tractable then. Great. Are there any other questions from the audience, either here or in the great?
Yeah, this may not be in your purview, but I'm just thinking, sort of projecting myself being in this spacecraft, getting farther and farther away from the Earth. I mean, at least if you're in a submarine, you know that people are nearby or water on your own Earth. And you're on the moon, you can see the Earth, but here these people are hurtling. I mean, we know how big Mars is from here. Imagine you're halfway to Mars and you're just in space. And I'm sure people have thought about what's going on in the minds of the people on this craft. I was thinking to the point where maybe they should carry firearms or something and handcuffs. Crazy. I just, I'm just sort of speaking out loud. It doesn't have anything to do with your talk, but there must be people that are working on the psychological aspects of people who've been gone for so long. I'm just wondering if you had any ideas or people even talked to anybody about that kind of thing.
I don't know if you heard that, Alonso. He was asking about the psychological aspects.
So far away.
Yeah, from being so far away from anywhere for such a long period of time and being unable to get back in a very long period of time too. He said he knows that's outside of your area of expertise, but he's asking what might have been considered about that.
Yeah, so there's research, and in fact, at Johnson Space Center in Houston, there's something called the Human Exploration Research Analog, and there was there were two now being integrated into something called the Mars Exploration Analog, MIA, and it's a habitat, and we're gonna take in a set of astronauts, not actual astronauts, right, but people who play astronauts for 2 years in there, right? And these have happened before, right? So there's one in Hawaii. I can't remember what the name of that one is. The Russians have done it, right? So these longer, you isolate groups, we call them mission analogs, and so a lot of work goes into understanding both the psychological state, the team effects, to the best of our abilities. And what's interesting is that the selection process for astronauts really is remarkable. And then you really do pick out a set of very remarkable humans, right? With and I'll say that I've had the pleasure, to work with quite a few astronauts, and again, exceptional, both in terms of the set of skills, the calmness under pressure, so it's a lot. And then, but just as an anecdote, I remember the first time I met a female astronaut, and I was like, holy moly, they're like twice as tough, right? I mean, it was just, in a very positive way. They were just so cool, so, and so able, right? And I don't know, maybe it's kind of the requirement of, kind of moving into a world that has historically been a male environment, but it, like, really all around remarkable, the last time that I think we put out for an astronaut, like an astronaut candidate call, you get tens of thousands of applicants, right? Obviously, and highly self-selected as it is, and so it's an issue. There's research. It's it's difficult, but again, a lot of self-selection in the first place, and then extremely good training, and then you're picking out a set of, again, like unusually healthy, unusually able individuals.
Great.
Thank you. Great.
Question?
It does seem like there's a time period in which they might be thinking that they will go out to Mars. Hearing like that, and also, when you hear about Elon Musk doing something going to Mars, do these guys work together?
So the question was, what's the? Oh, Greg's asking me to move away from the camera. The question was about the time period for an actual mission. What's the time period being considered now, and also asking about the Elon Musk SpaceX effort, and how that fits into all this too. If there's any how that relates to this work as well.
Yeah. So we launch to Mars about every 2 years, right? When as Earth comes up, as I said at the beginning, right, as Earth kind of comes up, catching up to Mars in its orbit, and then so but this is now going back a year or two. I haven't seen it, but we're looking at, like, in the, say, late 2030s, early 2040s, as kind of like that's what we're working toward as we develop the Mars architecture, and like look at these technologies that are now, we're kind of just kind of starting down the path of some of them, and at the radiation shielding and all these pieces, right? And so that let's call it ballpark 2040, for NASA. Elon Musk was, until quite recently, right? So I think you probably saw, right, that SpaceX just in the last 2-3 months said, okay, no, we're going to go set up a city on the moon. But until before that, the idea was humans to Mars. I think it was 2031, and then begin to settle Mars 2032, right? And we met with them, maybe, about a year ago on this, not with Elon Musk himself, but with SpaceX, and to talk about this, and their plan was, and I don't know what it is right now, but to send a Starship, an empty Starship, like, again, like nothing in it, toward Mars, right? I don't know if that's still the plan, but I'll say that from our understanding, and from talking to them and working with them, the challenges are similar. In some ways, by the way, like, SpaceX has done remarkable things, right? Like, the landings and the chopstick catching of the first stage as it comes back down. And these are the advances that are brought about by building rockets, designing and building rockets in the computer age, right? Our last set of rockets were, in a sense, were like literally like developed in the engines, et cetera, before this, right? And that's so like I focused on sensors, but this point that effectively that as we go forward, really our entire systems need to be, computers and data. We need to start in a sense from that part of the concept, right? Because that's where the kind of the power is for resilience. And so I think again, I think SpaceX has basically what NASA's role, any like the government agencies that are in this kind of research and technology business, the role is to advance the area to the point that then it can be commercialized by American companies, right? That's the the business that we're in. And so low Earth orbit, supplying the space station, et cetera, is something that is a done thing. So then you hand it over to industry, and because it's no longer exploration, it's no longer kind of the new frontier. Having said that, both SpaceX and Blue Origin have the contracts for building and delivering the human landing system for this next moon mission. And so the partnerships between NASA and the space companies, and it includes Boeing and Lockheed, some of the ones that go back farther, but also the new ones, continue to be strong, right? Like as it always has been.
Great. Other questions? Or anybody else online? Don't see any here. None online.
There are people on it.
But no questions. Okay. Well, thank you very much, Alonso. Appreciate your talk very much. Fascinating. And let's give him a round of applause.
Thank you. My pleasure. Thank you for all the good questions.